So section 9.1 is on determining probabilities. So the study of probability came from a desire to understand games of chance, like those involving cards or dice. Probability has since become useful in fields like insurance, marketing, polling, investment decisions, experimental drugs. Probabilities have a whole slew of uses. Gambling, things like that. So only grade 7 has specific Common Core standards for probability. So that's like the lowest grade that you're going to find some Common Core standards for probability. So probabilities are ratios that are expressed as fractions, decimals, or percents that are found by looking at outcomes of an experiment. Okay? Now, let's define a few other terms. An experiment is an activity where the results are observed and recorded. No big deal, right? An experiment sounds like it's going to be something super scientific, right? Involving a lab coat and some glasses and some test tubes and stuff, but it's not. An experiment can be something as simple as just flipping a coin 50 times or rolling a die 100 times. Yeah. An outcome is the result from a single trial of an experiment. Okay, so an experiment gives you outcomes, these results or these outcomes. Okay. The set of all of these outcomes in an experiment is called the sample space. And then any subset of the sample space is called an event. So we just need to make sure that we get our terminology down. A lot of students mistakenly think that event is the same as outcome, and it's not. It could be a single outcome. It's possible for an event to be a single outcome, but it doesn't have to be. It's any subset of the sample space. Okay. So let's dive right into an example. Let's determine the sample space for rolling a 6-sided fair die. Now remember, the sample space is the set of all of the possible outcomes. So let's go back to this. So if we're rolling a 6-sided fair die, the outcomes, and this is a set, the set of outcomes would be a 1, 2, 3, 4, 5, or 6. So we're talking about a standard 6-sided fair die. We know those are labeled 1 through 6. It's not possible to get a 7 or a 12. And this is a set, so I use these little braces here to denote that it's a set. Okay. Next up, flipping a fair coin. Well, that one's got a pretty easy sample space. It's either heads or tails. Rolling an 8-sided fair die would be the numbers 1 through 8. And yes, such a thing does exist. I have students ask me if that even exists. It does. The die doesn't have to have 6 sides. Flipping 2 fair coins simultaneously. So they could both land on heads. One can be heads and one tails, one tail and one head, or both tails. And then choosing a marble for a bag that contains 3 red marbles and 4 blue marbles. Now this one, you might think that the sample space is going to be red, 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 blue, 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 blue. You could consider that to be the sample space. But typically we use something called the fundamental sample space, okay, which is the smallest possible representation. And in which case we would just say, just red, just blue. We don't need to repeat it. It doesn't matter how many times it shows up. Now, this number of marbles does affect the probability, as we'll see later, but this is the sample space that we're going to want to use, that fundamental sample space, or the smallest possible sample space. All right, so example 2, we're going to list an event associated with each of these. I'm trying to get all this on one page here. Now remember, event is just any subset. So you got to remember, you got to dig deep in your brain here. That was way back at the beginning of Math 200, right, where we talked about sets and subsets and stuff like that. So any subset, there is a slew of correct answers here, okay? So that's why I said list an event, not the event, because there's not just one. There's a whole bunch of them. So if we're talking about a fair die with 6 sides, an event could be, like, let's say you roll an even number, 2, 4, 6. Okay. Or let's say that you roll a, I don't know, a prime number, 2, 3, 5. Let's say that you roll just a 4. Or let's say that you roll a 1 or a 6. So you don't have to have a certain number of elements in an event. You know, I can have 1 thing, 2 things, 3 things. I could have all 6. Remember, the set itself is considered to be a subset. Okay, so pause the video and then see if you can come up with an event to go along with each of these up here. Okay, so an event here would be like, you know, just heads or just tails. Now really, you can just put one of these answers and be fine. I'm just giving you a bunch of examples. An event for rolling an 8-sided fair die, it could be the numbers 1 through 7. So for this one, your answers can vary. You know, you could have like, okay, I'm just going to roll a 1, 3, 5, or a 7. So for D, flipping 2 fair coins, okay, well, let's say that an event, some subset, would be getting 2 of the same things. You know, 2 heads or 2 tails. And then the red or blue, let's say that just red, or just blue. Or remember, you can use itself here. That's considered a subset. Alright, so just a little side note here. An outcome is a single result. Okay, now I know I'm defining outcome by using the word outcome. Outcome is a single, let me just change that to result. Well, I don't know. Single outcome, whereas an event can be a single or multiple outcomes. So, let me just kind of put them here. So single or multiple ones. So I just wanted to point out the difference between outcome and event. An outcome is just one thing. So when we talk about the different outcomes here, that's just one result at a time. An event can be just one result, or it could be a bunch. It could be 2, it could be 3, 4, however many, you know, or even all of them. We are going to talk about 2 types of probability. Okay? We're going to talk about experimental probability, which is, excuse me, sometimes called empirical probabilities as well. Now, they're formed by actually doing an experiment and recording the results. That's why, even though some books tend to use empirical probability a lot, I prefer the term experimental probability because I think it's a lot more descriptive, right? The experimental probability is about conducting experiments. And then we have the theoretical probability. Also, some texts call it classical. That's the ideal, right? The theoretical probability. In theory, what would it be? Now, this disregards physical or material imperfections. So, if you're talking about flipping a coin 100 times, theoretically, it would land on heads half the time and tails half the time. Now, we know that experimentally that may not happen. It may land on heads 40 times and tails 60 times. So that's those slight differences. So just so you know, in this chapter, whenever you see the word probability, it means theoretical probability. So we don't actually want you to do an experiment. We're going to use the theoretical probability. Now, there are instances where we would rather have actual data. You may think, well, why am I even talking about experimental probability? Who cares? Just use the theoretical one all the time, right? Now, there's actually times when you would want the actual data instead of a theoretical data, right? You actually want, actual numbers. Like, for instance, I looked these up for you, so, you're welcome. Actual data. Not kidding here. The probability of you being killed in a plane crash is 1 out of 1 million. By lightning, 1 out of 3 million. By a shark, 1 out of 100 million. In a car accident, 1 out of 7,000. Now, you know what? This kind of stuff right here, I know my dad never got on an airplane, ever, his entire life. Never got on an airplane. He's like, nope, I'm not getting on an airplane. Those things crash. I'm like, you're much more likely to be killed in a car than you are an airplane. But I couldn't convince him of that, which I can kind of see, right? I mean, if there's a car accident, it's more likely you're going to survive, right? Because at least you're on the ground. If there's a plane accident, I don't know. So I kind of got where he's coming from, but I still have my data there. From a heart attack, 1 out of 400. And when I was looking up the data for being killed by a shark, this showed up, being killed by a cow. I don't know about you, but I'm shook. I am shook by that number. So you mean to tell me I'm more likely to be killed by a cow than a shark? Yeah. Apparently so. I want to know who these people are that's being, murdered by cows. But is it trampling? Is it what? How are these cows killing people? Anyway, so yeah, I've got questions. But yeah, I thought you'd be interested in that number too. Now, there's actually people whose job it is to come up with it. Oh, look, hey, I put it up there. There's people whose jobs it is to come up with this data, right? They work for insurance companies, and they calculate these probabilities and stuff. They collect all this, this data, and so they're called actuaries. And what their job is for insurance companies when they decide, how much to charge you for life insurance based on your age, whether or not you smoke, whether or not you, I don't know, do cocaine regularly, things like that. That they come up with numbers as far as like, okay, how likely are you to die? And then that's how they determine your, life insurance payment amount. How much you got to pay. Anyway, these people are called actuaries, and they make some sweet bank. I'll tell you what. Actuaries make some sweet, sweet money. Probably should have pursued that more. Anyway, but no, we don't want the sweet money, do we? Because we want to be teachers, so we want to be poor. Anyway, back to the theoretical probabilities. The probability of an event. So we write it like this, like probability of E. I don't know if you guys remember when we talked about functions way back in algebra. You know how we wrote f of x? Well, that's what this is, the probability of E. That's not multiplication. Okay, that's just notation. So the probability of an event is the number of outcomes in an event divided by the number of outcomes in the sample space. So that's the notation for it. That's how we write it in abbreviated math language. I wrote everything out for you over here too. And you can see I kind of highlighted this in blue so that you could find it easier, because this is a formula that we are going to reference a lot. Now, we could also write this, probability as the probability of the first outcome plus the probability of the second outcome, an event all the way up, where these are all the outcomes in an event. That's just a lot more cumbersome to have to write. So let's just dive into example. So you roll a fair six-sided die. Now, why do I keep saying the word fair? Well, what is an unfair six-sided die? Well, that would be a die that had fours on all sides. Right? That would be an unfair die. So we say a fair six-sided die has the numbers 1 through 6. And another way for something to be unfair when it comes to a die is if it's weighted. So a weighted die, when you roll it, if there's, say, like a little bit of extra weight inside of it, it'll always, land on that weight, right? That weight will kind of weigh it down so that it always lands with a certain number up. So if you think about dice games, like craps, that kind of thing, you want those die, you want every number to be just as likely. So anyway, let's find the probability of rolling a 1 or a 6. All right, well, coming back up here, the number of outcomes in the event. So my event is getting a 1 or a 6. The number of outcomes in my event. I'm over here thinking, do I want to write over here? No, I need that space. Over number of outcomes in the sample space. The number of outcomes in the event was 2, 1 or a 6. So there's 2 ways to get either a 1 or a 6. Either you get a 1 or you get a 6. What is the sample space? How many outcomes are in the sample space? Well, it's a six-sided die. So it's 6. So 2 numbers, that's 1 or a 6, 2 numbers. And then we have 6 total. Now this does reduce, so you can reduce that to be 1/3. And my lab is going to expect you to reduce those fractions, but I think I've got it set for a tolerance of, being okay if you don't reduce fractions, but I'm not 100% sure about that. I was kind of iffy about that when I checked that box as to whether or not it stayed checked on every single assignment that I created. No. A number less than 5. Now, I'm going to go ahead and read the next question too, because I want to point out the differences between those. These are very subtle. A number 5 or less. A number less than 5. These are 2 different events. Less than 5 doesn't include 5. So a number less than 5 is 1, 2, 3, or 4. A number that's 5 or less includes 5. So that's 1, 2, 3, 4, 5. So for this event, we have 4 possible outcomes, still out of a total of 6. So we're still going back up here to the total outcomes in the sample space. That reduces to be 2/3. This one we have 5 outcomes in the event and 6 total in the sample space. So we get a total probability there of 5/6. Okay. So I do number the pages so that you can kind of keep up with how much more we have to go. So you can see that we're like halfway done. So you roll a pair of fair six-sided dice. So die is singular, dice is plural. let's find the probability that the sum of the numbers facing up is 5. All right, let's talk about the sum. What are the possible outcomes? Okay. So you roll a pair of fair six-sided dice, find the probability that the sum is 5. How many ways are there to get a 5? Well, let's see, you can get a 1 and a 4. You can get a 4 and a 1. You can get a 2 and a 3, and a 3 and a 2. Is that it? I think that's it. So we have 4 outcomes in this for this event. How many total outcomes are there for rolling 2 dice? Ooh, that one's kind of tricky, isn't it? That one might take some thought. So what's the total number of outcomes in the sample space for rolling 2 dice? You might think it's going to be 12, right? Because you think 6 plus 6. But it's actually 36. It's 6 times 6. So you start thinking of all the different outcomes of rolling a pair of six-sided die. So you can have a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6. You can have a 2 and a 1, a 2 and a 2, a 2 and a 3, 2 and a 4, 2 and a 5, 2 and a 6. You see what I'm doing here? 3 and 1, 3 and 2, 3, 3, 3, 4, 3, 5, 3, 6. There are 36 outcomes for rolling a pair of six-sided die. And we learn in a later section why it is that you can just easily just multiply 6 times 6 to get that 36. All right, so we get 1, 2, 3, 4 outcomes that'll give me a sum of 5 out of 36 outcomes, and that does reduce to be 1/9. A sum that is larger than 7. Okay, now that doesn't include 7. So we're going to have to do some counting for this one, okay? So let's talk about a sum of 8. Okay, well, let's see. Can we get a... No, we can't get a 1 and a 7. That's not possible. So how about a 2 and a 6 and a 6 and a 2? That'll give me 8. What else? 4 and 4. Now we don't need to repeat this. A 4 and a 4 is the same as 4 and 4. Ooh, 3 and 5. 5 and 3. Now that's all for just 8. We still got to do 9, 10, 11, 12. Gosh, how much higher is this? This might be really awkward to have to count, right? So I'm thinking there's got to be a better way. And it turns out there is. I'm just going to gently scratch this out to show you that I started with this and I was like, yeah, no, let's not do that. Okay. So I wanted to start with this just to kind of point out that this was going to be a hot mess.